Let's think for a second about the absolutely colossal forces at play, miles and miles beneath our feet. We're talking pressures that can crush steel, squeezing rock with the weight of entire mountain ranges. Well, today we're going to pull back the curtain on how engineers can actually see into this invisible world, and how they predict and manage these incredible forces.
You know, it really boils down to this one question. When you're drilling a well for energy, whether it's oil, gas, or even geothermal, you're basically performing incredibly precise surgery on a patient you can't see, from miles away. You can't just look, right? You have to predict how the rock is going to react to every single thing you do, and believe me, the stakes could not be higher. Because when you get it wrong, the consequences are catastrophic. If you misjudge the forces, the wellbore can literally just collapse in on itself, trapping millions of dollars of equipment. Or the rock can fracture and you start losing all of your expensive drilling fluid into the earth. And worst of all, you could get a high-pressure kick of fluid into the well, which is the first step toward a potential blowout. So yeah, flying blind is just not an option.
To solve this huge problem, engineers needed a way to see the unseen. They needed a kind of blueprint for the Earth's mechanics, a predictive tool that could tell them exactly how the subsurface was going to behave before they even started drilling. And that led to the development of something truly remarkable. It's called the Mechanical Earth Model, or MEM for short, and it is absolutely brilliant. The best way to think about it? It's like a CT scan for the Earth, or maybe a weather forecast, but for rock. It's a predictive digital twin of the subsurface that pulls together geology, rock physics, and stress data to build this incredibly detailed picture of all the forces at play. It's the tool that turns that blind surgery into a guided, predictable procedure.
So, how does it work? Well, the first key ingredient is understanding the planet's natural grip on the rock. We call this the in situ stress. You've got one vertical stress, which we call S sub V, and that's really just the immense weight of all the rock above it pushing down. Simple enough. But then you also have two horizontal stresses from the constant crush of tectonic plates. And as you can see, we label those SH max and SH min for the maximum and minimum horizontal squeeze. But there's a force pushing back. See, inside all the tiny little pores of the rock, there are fluids, water, oil, gas, that are also under immense pressure. This is the pore pressure, and it pushes outwards, working against the squeeze from the outside. It's kind of like the air inside a balloon pushing against your hand as you try to squeeze it. And this right here is the crucial point. The rock skeleton itself doesn't actually feel that total crushing squeeze. What it really feels is the effective stress. That's the big squeeze from the outside minus the push from the inside. This net force is what determines everything. It's the magic number that tells you if the rock is going to hold firm or if it's going to crumble. Getting this balance right is the whole game. So how do you actually build one of these incredible digital twins? Well, it's a lot like assembling a super complex puzzle, using pieces of data that come in all different shapes and scales. So where do we get the puzzle pieces? Well, looking at the table, we start with the really big picture, 3D seismic data, that gives us a map of an entire basin. Then we zoom way in, right to the wellbore itself, with something called wireline logs. Think of them as tiny scanners measuring the rock foot by painful foot. For the ultimate ground truth, we actually take physical core samples back to a lab and literally crush them to measure their strength. And finally, we confirm everything with well tests that directly measure the forces way down in the hole. The MEM is the brain that puts it all together. Okay, I know this slide might look a little complicated, but it's really just a simple, logical recipe. Step 1. You figure out the vertical stress just by adding up the weight of all the rock. Easy enough. Step 2. You define the rock's personality. Is it stiff like granite or brittle like chalk? Then, in step 3, you estimate its breaking point. And finally, and this is so important, you use real-world data from well tests in steps 4 and 5 to fine-tune your model and really nail down those tricky horizontal stresses. See, each step just builds on the last one.
Now here's one of the really fascinating challenges engineers face. The stiffness you measure with high-frequency sound waves from a log, that's a dynamic measurement, is almost always higher than the stiffness you get from slowly crushing a rock in a lab, which is a static measurement. Why? Well, the sound wave travels so fast that the tiny, microscopic cracks in the rock don't even have time to react. So you have to be really careful to calibrate between these two different worlds to build an accurate model. But what about all those old wells drilled decades ago, before we had all these fancy logging tools? You're often missing critical data, like the sheer sonic log you need to figure out a rock's stiffness. This is where modern tech comes in with a seriously elegant solution: machine learning.
By training machine learning algorithms on wells that do have complete data, we can literally teach an AI the complex relationships between all the different rock properties. The model then learns to predict the missing log data with just astonishing accuracy. We measure that accuracy with something called an R-squared value. All you really need to know is that a value over 0.9, like you see here, means the AI's prediction is nearly identical to what a real tool would have measured. It's like having a time machine for data collection. It's incredible.
So we've built this incredibly complex, data-rich digital twin. Now for the really fun part. What do we do with it? Let's take a look at how the MEM delivers tangible, high-impact results out in the real world.
Its #1 job, its primary mission, is to ensure wellbore stability. The MEM calculates what we call the safe mud weight window. This is the very precise pressure range you need to maintain inside the well. If your drilling mud is too light, the borehole will start to collapse. If it's too heavy, you'll actually fracture the rock. The MEM defines that perfect Goldilocks zone to keep the wellbore intact, preventing stuck pipe and saving millions.
And this is just brilliant. It's like a real-time diagnostic tool. Engineers don't just blindly trust the model, they verify it. They actually look at the shape of the little rock fragments, the cavings, that come back up to the surface. As you can see in the table, if they see angular, splintery pieces, they know the mud is too light and the well is starting to collapse. If they see these long, concave slivers, they know the mud is too heavy and they're fracturing the rock. It's a direct feedback loop from the rock itself, telling them what's happening 2 miles down. The second huge application is in hydraulic fracturing. Now, the old way was what we call a geometric design. You just place fractures at fixed intervals down the well, assuming all the rock is the same. The result? Some fractures would take all the fluid and energy, while others did nothing at all. But the MEM allows for an engineered design. You use the model to find zones of similar stress and brittleness and place your fractures there. That way you ensure every single one is effective.
And the impact of this change, it's staggering. Studies have shown that shifting from that old brute force geometric approach to a precise, MEM-guided engineered approach can increase the total production from a well by over 60%. That is a massive, massive return on investment, all from just understanding the rock's mechanics.
And finally, the MEM helps manage a problem that can literally kill a well: sand production. See, when you produce oil or gas, the pressure inside the rock drops. If it drops too far, too fast, the rock matrix can actually fail, and tiny sand grains will start flowing into the well. This erodes equipment and eventually just chokes off production entirely. The MEM calculates what's called the critical drawdown pressure, basically the absolute speed limit for production to avoid that from happening.
So what's next on the horizon? Well, the mechanical Earth model isn't a static photograph of the subsurface. The future is a model that is alive, one that learns and evolves right alongside the operation itself.
This is the idea of the living MEM. It's a system that streams real-time data directly from the drill bit, using AI to constantly update its predictions and reduce uncertainty with every single foot drilled. So this isn't just a forecast you make before you start. It's a dynamic, intelligent guide that is continuously optimizing for safety and peak performance as things happen.
Which kind of leaves us with a final thought. The mechanical Earth model is this powerful testament to our ability to model, to predict, and ultimately to engineer these incredibly complex, invisible systems. It really makes you wonder, if we can create a digital twin of the very stresses holding our planet together, what other hidden worlds, from our climate to the human brain to global financial markets, are we on the verge of decoding next?